So our next speaker is Sarfaraz. He is in IIT Bombay and he will talk about fair allocations under Laminar Matroid constraints.
Okay, good afternoon. I'm Sarfaraz Equbal and from IIT Bombay. I'm going to talk about fair allocation under Laminar Matroid constraints, EF1 for 3 agents. So we'll start with fair allocation. What is fair allocation? I think most of the thing Yaswant already told. We have set of agent, then we have set of items. We wanted to, and we have valuation function for each agent for each item. And the goal is to divide the items such that every agent feel they are in fair, they get a fair share. So the fair allocation under the unconstrained setting is like a very well-known problem, and we have in context of when we are looking into the fair notion as envy-freeness or envy-freeness up to one item, it is known from like in 2004 only by Lipton. Let's say for additive valuation, we have there is always exist an EF1 allocation. And the technique to find this allocation is there are like two basic technique to find this allocation. One is greedy round robin proposed by Budesh at 2013. It says like we have an order of agent, and each agent goes according to order and pick the best item that they have, remaining items. And the next technique is like envy cycle elimination technique, where if we have an allocation, we will create a envy graph out of it, and according to and then if there is a cycle in the envy graph, we will remove the cycle, and then we have in topological order the agent that is in the list of in the topological ordering. We will allocate the item to the agent, and similarly then again we remove the cycle and do the same process repeatedly. So this yeah, but this envy cycle elimination will work for monotone also, but it's also work for EF1. But in the constraint setting, what we know. So, but what does it mean by the constraint setting? When we are looking into when we are putting some additional rule that restricted the allocation, that which allocation is feasible and which is not. So in this direction, there are multiple examples for the such as like cardinality constraints. When we are limiting the number of items for such category, like if the items are in category, how many items an agent can get from the such categories. There are like general Matroid constraints where we want the bundle allocated bundle is the independent set for the Matroid. Similarly, we have the connected graph constraints where the items are in the graph and the allocated set must be a connected part of the graph. But we are looking into for the today's talk, we are looking into the Laminar Matroid constraint. This is a definition, but I'm not going into detail of this definition. So we can understand this constraints by example. So this is the example of Laminar Matroid constraints where we have a set of items, and items is divided into the categories, and further the categories is divided into subcategories, and it can be finite length tree. So this is basically the Laminar family structure, and the constraint is defined on every nodes of the graph. So node of the tree. So like for example, we have some constraint on the computers, and we also have the constraints on desktop and laptop. So this whole family, Laminar family tree have a limitation on each node. That is basically the Laminar Matroid constraints. So what are the known result in term of constraint setting? So the one of the best nice results is by Barman and Biswas. It says like for the cardinality constraints, EF1 always exists under the cardinality constraints for the additive valuation. And for the Laminar constraint setting, the EF1 exists for identical additive valuation. In the same paper, they have these two results. In the similar line of results, the Feldman in 2023 gave set of results for the cardinality constraints with heterogeneous Matroid constraints. Here, the heterogeneous Matroid constraints means like every agent have a different limit on the number of on the each category. So this is different to the cardinality constraints. In the heterogeneous Matroid constraints, the notion of EF1 is like then it's need to be tweaked, and then they have some notion of FEF1, and they prove for the if there is only two categories, then FEF1 is exist for the n agents. Yes, and for identical additive valuation, EF1 always exists. But for additive valuation, the EF1 exists for only for two agents. So the result is open for more than two agents in the cardinality constraint under the heterogeneous Matroid constraints. Similarly, here they have also results on the base orderable Matroid. Basically, the base orderable Matroid is some set of Matroids. Under that, the Laminar Matroid and the partition Matroid or the cardinality constraints is also under the base orderable Matroid. So any result that is true for the base orderable Matroid is also true for the Laminar Matroid. And in this set of result, they prove that if the valuation is binary, then we have EF1 allocation for the three agent. And for identical additive valuation, the EF1 exists. But for the additive valuation, the allocation is only for two agent. EF1 allocation exists for two agents. So basically, if you can see any additive general additive valuation, we have only results for two agents case. So like from there we started looking into the Laminar Matroid case for the three agent. Okay, but before going to the Laminar Matroid case, I wanted to emphasize the cardinality constraints result by Biswas Barman. What is this? Like the setting is like we have a set of item that is divided into categories C1, C2, CL, and each category have a threshold value Ki. And goal is to find EF1 allocation that is also feasible under this threshold. There is a one assumption, and we require it because like the threshold must be greater than the number of item in the category divided by number of agent. Because if we wanted to allocate the item completely, otherwise we cannot. We may have to leave some items unallocated. So this is kind of requirement. So the idea of this algorithm is very simple. We are going one by one to each category, and we run the round robin algorithms on that category. Then we merge this allocation that we get from the specific category, and merge it to the previously allocated item, and then we do the envy cycle elimination on the partial allocation. From that, then we will get an acyclic envy graph, and then we have a topological order. And using this topological order, we will go to the second category and run the greedy round robin again. So this basically we are going one by one to the category, and in between we are removing the envy cycle. So why this is the feasibility is easy to see because we are running round robin. So each agent will get equally number of item, and at most one an agent can get at max one extra item, and that must be lower than the ceilings of number of item on that category by n. So then what about the feasibility? Why envy free? Because when we suppose we have an allocation that is partial allocation is envy free, and according to algorithm we are running the envy cycle elimination. So the topological order we have after the envy cycle removal, let's assume like the A is preceding B in that order. So because this we are running round robin after on this ordering, the agent A will not envy B in this round robin, and in the previous allocation, because it is EF1, if agent A is envying B, then removal of one item will envy will stop the envying. So merging these two allocation will give us the EF1. And in the if you are looking in the opposite way, like if B is preceding A, then the A will not envy in the partial allocation, and A may envy in round robin allocation, but merging will stop envying. So this allocation will be EF1. Now, I wanted to say why this same algorithm will not work for Laminar Matroid case, because it looks simple, because the category here is in the cardinality constraint we have categories, and in this case we have subcategories also. Because when we are trying to satisfy the category for the threshold for the children case, it may fail the threshold for the parent case. We have an example, but I don't think I have time to explain this example. If anybody want to, I can talk about it later. Yes. So then the Laminar Matroid case for the for the two agent we have results, but we have an alternative alternate algorithm that is easy to extend for the three agent. So I will first explain this. The algorithm idea is very similar to the cardinality case. Here what we do, like we will process the items from the bottom to the top. And what we do, we will allocate the items until it is evenly distributed between the agent. And because of this, if the number of item in the category is odd number of item, then we may have to leave one item unallocated. In this way, like we have distributed all the items evenly in node. But if the node is internal node, so that means like they like their children have leftovers. If there are multiple leftover, more than one, then we will evenly allocate that leftovers in the agent using the round robin algorithm. And if we required, we will left over one item and pass it to the parent. So for each node, we are allocating only the even number of item, and if required, we will left one item unallocated and pass it to the parent. And similarly, we after each allocation, we will do the merger and then envy cycle elimination with the and then we update the topological ordering of the from order of the envy graph and do the same thing till the root. Why this allocation is EF1? Because of same reason that we have for the cardinality constants. We are doing nothing but the round robin continuously, and in between the two round robin, we are doing the envy cycle elimination. So it will be EF1. And why it will be feasible? Because at each node, if you see, the items are at most one item will be unallocated, and the other item is equally divided between the two agents. So each agent is having equal number of item, and one item is only unallocated. And at later phase, we allocate that item to one of the agent and then that means the difference between the two agent for a particular node is at most one. And this is like naturally it will satisfy the feasibility criteria of this. So the two agent case was very similar to this, but when we extend this same algorithm for the three agent, the problem is now we have leftover of 0, 1 or 2 items. So we have to handle this leftover, we cannot directly handle this similar way in what we do in two agents. So how we will handling this leftover, that is the tricky case. So in the case of what we do in this case, we are not just passing the leftover as it is, but we are passing the leftover as bundle of the items. So if an agent and in the category, if 2 items left, we are passing it as the bundle of 2 items. So and then what we will do, if there are multiple bundles and the subset of it, if there sum of this subset is 3 is equal to 3, then we will run the round robin on this bundle, this subset. And similarly, we merge it to the partial allocation. Then further we remove the envy cycle and do again for the other set of 3 items. but it may possible because there are 0, 1, 2 items, so there may not be this 3 size subset, but the size set is 6. So if there are 6 item in the set, we cannot run greedy round robin because it may allocate two items from the same group to the same agent. So we have a special 6 item allocation that will run in this case. And then similarly, we will merge the allocation and then update. And the leftover items is passed as the bundle. That is like if there are 2 items left, we will bundle it and pass it to the parent. Okay. Now what we required from the this special 6 item allocation, because we have 6 item and the property we want is like the each agent must get exactly 2 items from these 6 items because we want equally division. And then the feasibility, like no agent will get from the 2 item from the same bucket. And in the fairness notion, we want the envy-free in the direction of in the ordering forward direction of ordering, and EF1 in the reverse direction of ordering. So if we have these 3 criteria for this allocation, then we can say like EF1 exists for 3 agent because the property I have defined is nothing but the property of round robin. When we run round robin in the forward direction, we have no enviness, and in reverse direction, it may be EF1. So if we have a location that is fulfilling that property, then we can have EF1. Yeah, because but it may possible like 3 subcategory have left 2 items. Now you allocated 3 items from the that, and the 1 item from you left 1 item from that category, and that the 1 item that you allocated is allocated assuming like agent A. Now in different next time when you allocating that item, that same 1 item can go to the same agent, and now an agent can have 2 extra items from that category. Uh, yeah, I have slides for that. But first we will see the how feasibility will fulfill, just because like the same way, if we have left 1 or 2 item, the total because we are dividing equally, the each agent will get mod s minus 1 by 3 or mod s by 2, and that is like simple mathematics. We can check it and it will work. But the yes, for the 3 agent, yes. So for because we were time was not permit, I put it that slides on the extra slides. Can I show you, or we can talk later? Okay. So the future work is like we can extend this algorithm for the 4 agent or more agent, but for handling 4 agent, we have like a special pattern of like allocating 3 for time, like 3 items or 3 items. If we can handle this kind of pattern in the leftover items, so we can have for more like 4 agent and more agent, 4 or more agents. This is for 4 agent. Oh, I didn't get, but oh, for cardinality constraint is for n agent. And we can explore for the different kind of fair notion, or we can talk about it. That's all. But if you want, I have this extra slides. If no, okay.
Anyone has some questions?
That's like okay. Feasibility. what will happen like at each node when we are at the just assuming like on the list node they are we are dividing we are running round robin
For
and
each of those,
yeah
each of those, what is this
each
categories?
of agent will have like a equal number of item and at most one item will be left over.
Right.
And later what we are doing, we are allocating that one item to any of the agent and the difference must be only one difference. And if there is different one, then like this criteria will be satisfied naturally, because like if one agent have extra than s by mod s by 2 plus 1, then other agent must have s by 2 minus 1. That cannot be like the difference is 2. So if the difference is 1, they cannot be greater than mod s by 2.
Right. But then how do you
Yeah,
use that for the upper level?
Yeah, for intermediate level, the children, just assuming like for the like we can think about induction hypothesis. At the base level we are true. At the induction level we assuming like at the level we are at most one item left. So in the upper node, all the children have evenly distributed item, and the leftover is when we have leftover, we are again running the round robin. So on the leftovers. So leftover is also again divided by the two agents. So overall, we have divided the agent items into two parts, and one at most one item can be left.
No, if no more questions, then let's thank the speaker.